Hello everyone, myself Piyush and TANDEL working as Assistant Professor in Electrical Engineering Department of Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. And the name of subject is Industrial Instrumentation, which comes in 4th year 7th semester. Right now we are discussing the chapter number 2, that is strain gauge and strain measurement, and this is the last module or last video of chapter number 2, that is 2.6. So let's start with flow of content. So in this video lecture we are going to see the strain gauge balancing circuit for semiconductor strain gauges, temperature compensated gauges, compensation through the bridge arrangement, application of the strain gauge, and strain gauge calibration. Now we are going to study all these topics in detail. So let's start with the first topic, that is strain gauge balancing circuit. Now as the name indicate, we are balancing our circuit using the strain gauge. Right now the strain gauge measurement can be done by different methods. Okay, depending on the method that is used, the balancing circuit is going to be used. Okay, so we are right now talking about two different method, and the first method, that is called as a out of balance, or we can say that direct reading type. So we already know the type of Western bridge. Okay, in that Western bridge only one arm, that is called as a R1, R2 or R3, R4, right? So any of the arm, let's consider the R1 is going to be connected with the strain gauge, and we can directly measure that change in strain, or we can say applied in strain with respect to change in resistance. In this circuit, the output voltage varies as a result of strain are calibrated directly in term of microstrain. Right now we need to understand it is in microstrain, and this measurement is done for dynamic strain measurements and static strain measurements. Error is possible in excitation voltage variation and gain instability of the signal amplifier. So the value of signal that we are getting from the out of balance bridge, or we can say direct reading type, is very small, and we need to amplify that reading, okay, for better understanding. So at that time error may be introduced into our system. And the second method, that is the second method of measurement is using a null balancing bridge, where a resistance of one or more arm, the resistance of one or more arm of the bridge is varied to match the change in resistance. Whatever the resistance is changing whenever we are applying the strain at a strain gauge, so we need to balance our bridge with respect to that applied strain. So for that we can also use one or more than one resistance to balance our bridge. It is suited for static measurement, that is shown in figure. Let's see the figure first. So over here, as you can see, the figure of balancing Western bridge circuit, or we can say null balancing type Western bridge circuit. The reading of bridge is independent of the excitation voltage and gain of amplifier. Okay, the accuracy of the measurement is high because right now we are changing the resistance of other arm to match the change in resistance of the one arm. So the resistance R5 and R6, right now I don't think we can see R5 and R6. Okay, over here the point, from point A to starting point of the RP, we can consider at this point as a R5, and from point A to the end point of the RP we can consider it as a R6. Okay, R5 and R6 are part of calibrated potentiometer RP. So this is the calibrated potentiometer RP, and the calibration or the condition for the balance of this bridge is, we can say that the resistance of RAB, that is resistance between RA and B, that is R1, and resistance RCB, that is R3. So R1 R3 is equal to R4 R2, right? So whenever the condition is satisfied, at that time we can say that the bridge is in balance condition. Whenever the condition of R1 R3 is equal to R2 R4 is satisfied, then and then only we can call at this bridge as a balance bridge. So one thing we need to also notice over here, that is, suppose the resistance of R1 is directly connected to the strain gauge. Okay, so at that time what's going to be happen over here, point A to B, at that time right now we are considering R1 resistance, but here another resistance is also introduced, that is the R6 resistance. So the resistance between point A and B, that is R1 and R6, both are acting in between. So these both resistors are in parallel condition with respect to point A and B. So the equivalent resistance, or we can say the overall resistance of RAB, that is we can write as R6 R1 divided by R1 plus R6, because both the resistance are in parallel condition. Same we can also write on the other half side, that is the resistance between point A and point D. So over here R4 and R5, these two resistance are in parallel condition. So we can write RAD is equal to R4 R5 divided by R4 plus R5. Okay, so this is how we can calibrate our bridge, or we can say balance our bridge. Now we also know the strain, that is equal to 2 by G delta Rs by Rp into 1 by 1 plus delta R5 by R4. So as we can see over here, this equation can be read in terms of change in potential, or we can say potential resistance, that is at a point A. So right now in this figure we can also see like that over here one extra resistance, that is the R7, is also introduced inside of the circuit at a point of Rp, right? Rp, that is the potentiometer, or we can say calibrated potentiometer resistance. In this resistance R7 is also introduced, and the value of R7 is equal magnitude and opposite direction to the polarity of B and D. So whenever the output we are going to measure, it is in equal and opposite polarity, then we can say that our balance piston bridge is in balance condition. Right now we are balancing this bridge. In previous circuit we already stood, that is null balancing arrangement, and this is the balancing piston bridge circuit. Now we have also another piston bridge, that is null balance with additional bridge. Over here as we can see, here is the active bridge 1 and over here at dummy bridge 2. So why we require dummy bridge 2, that is the null voltage is obtained from the input source. Okay, whenever the null voltage is obtained from the input source, it cancel out the variation in the excitation. Okay, and when the active arm, or we can say this active arm 1, are subjected to the strain, the unbalanced voltage of the bridge 1 is balanced with the equivalence of, or equivalence with the opposite in phase voltage from a dummy bridge 2. By adjusting the resistance this IR5, we can change the dummy resistance of this dummy coil or dummy bridge and balance this active bridge 1. So initially and null balance condition or null balanced are obtained from the dummy bridge. This is the main advantage of the circuit. Okay, this is the main advantage of circuit. It is used in precise strain gauge measurements. Now next topic, that is the circuit for semiconductor strain gauge. A semiconductor strain gauge shows non-linearity in a gauge factor and a large variation of resistance. For good linearity in output voltage with respect to the strain, the condition required is to keep the gauge current constant. So this is the condition we required. Okay, so what is the equation of Ohm's law? That is V is equal to I into R. So whenever strain is going to be applied to our so whenever we are going to apply a strain, the value of resistance is going to be changed. But if the value of current is also going to be changed, at that time the variation in voltage is going to be very much large. So we need to keep the current constant to measure the actual strain applied on the strain gauge. The gauge current is kept constant by using the constant current bridge excitation or using a circuit that produces constant current in the bridge arm. Now the method of obtaining constant current is by introducing a high resistance in series with bridge excitation or using an optional amplifier in constant current mode. We can also use optional amplifier in constant current mode, or we can also thermistor is used to control the input excitation voltage so that it will give the constant current to the bridge arm. So whatever preference we are going to use, as per our application, we can choose any of method to give the constant current to our Western bridge, because we don't want any kind of errors in our reading. So whenever some amount of stress, axial stress, is going to be applied on strain gauge, at that time only the value of resistance is going to be changed and value of current is going to be constant. Then and then the value of voltage we can directly measure. Now we are going to talk about the temperature compensation. So different types of material have different types of characteristics regarding to the temperature. So if the temperature is going to be increased, the resistivity of the material is going to be increased or decreased depending upon nature of the material. So practically strain measurement are done for long period of time. Hence the gauge are subjected to change in ambient temperature. As a result, there is change in resistivity in the material of gauge and an apparent strain because of dimensional expansion of the gauge. So whenever temperature is going to be increased, the shape or the dimension of that gauge is also going to be changed, or we can say expand. Whenever the temperature is going to be increased, the gauge is going to be expand. The effect of change in ambient temperature is given as delta R by R, that is our change in resistance per actual resistance. Over here this is our delta T, that is change in ambient temperature, is equal to alpha S minus alpha G into G. Over here G is the gauge factor plus beta delta T. So delta T, that is change in our ambient temperature. Now over here alpha is the coefficient of linear expansion of the specimen, and we can also define this as a delta L divided by L0 into delta L. So it is going to be represented as a change in length divided by the actual length into the change in length. So that is called as a coefficient of linear expansion of specimen. Then after alpha G, that is coefficient of linear expansion of the gauge material, and it is going to be depend on the material of the gauge. And beta, that is the coefficient of resistivity of the gauge material. So this is how we can derive the change in resistance per actual resistance whenever we are going to change in temperature, that is whenever the surrounding temperature is going to change. Now next is temperature compensated gauge. Now effect of the temperatures need to be compensated, right? So if we are not compensating that value, it is going to be create error inside of our result. So the temperature compensated gauge comprise of two elements of different materials like constant and nickel, right? We are discussing about two different elements, that is constant and nickel. So the dimension of the material are selected such that the temperature induced change of resistance in one element can be nullified by the temperature induced change in the other element. So if one element is a positive temperature coefficient, so let's say that if the temperature is going to be increased, at that time resistance is going to be increased, the other material need to be negative temperature coefficient. It means that the temperature is going to be increased, the resistance need to be decreases, right? So we need to choose two different material, and dimension of that two different material are selected such that whenever the same amount of temperature is going to be changed for both the material, at that time the increase in the temperature, or we can say increase in the resistivity of the one material is equal to decrease in the resistivity of the second material. There and then we can nullify the effect of temperature in our gauge. As a result, there is minimum apparatus in strain. Okay, so this is how we can compensate our temperature change. Now moving forward, compensation through bridge arrangement. Okay, we already studied about the bridge arrangement. Now in a strain gauge measuring system, the temperature compensation can be obtained by correctly positioning the strain gauge. We can also compensate the effect of temperature by correctly positioning the strain gauge. The change in resistance is because of the two reasons. So main two reasons are the actual strain experienced by the gauge, that is what we need to measure, and the second, that is the temperature variation. So whenever temperature is going to be increased or decreased, at that time also the resistance is going to be increased or decreased depending upon the property of the material. But we actually require the actual strain experienced by the gauge. This is our actual result, and this is going to be produce some kind of error in our result, right? So for any strain, that is delta R divided by R, that is change in resistance divided by the actual resistance, is equal to delta R by R, that is E. For E, this is the actual strain applied by the gauge, and delta R by RT, that is the variation of the temperature. So overall change in resistance is summation of these two, both the difference, that is the actual force applied by actual force experienced by the gauge, and second one, that is the temperature variations, right? Now let's study two different cases. First case, let's assume that R1 is an active gauge subjected to strain being measured. Okay, we are in bridge circuit. R1 is the subjected to the strain that we are going to be measured, and R2 is the compensating gauge subjected to ambient as that R1 but not subjected to strain. So the material of the R2 is going to be different than R1. So the temperature effect of the R1 is going to nullified with the help of R2, but it is not directly going to experience the strain that is applied. Okay, only R1 is going to be bear that strain that is going to be applied, or we can say we are going to measure the strain. Now R3 and R4 are fixed resistors. Now the output voltage is given by V out is equal to V in P divided by 1 plus P whole square in bracket delta R1 by Re, that is the actual force that is applied on the R1 resistor, plus delta R1 by R1 T, that is the change in temperature. This is due to the change in temperature. Minus, why minus? Because we are nullifying the effect of temperature on R1. So minus delta R2 by R2T. So same amount of, the value of R1 by R1 and delta R2 by R2 is going to be neglect each other. So we can only get the actual force that is applied on the strain gauge. So if the R1 and R2 are same, then the result of R1 delta R1 by R1 is equal to delta R2 by R2. And if we are considering A, or we can say P is equal to 1 at that time, the equation is going to be like V out is equal to V in 1 by 4, because 1 plus 1 2, 2 square 4, 1 by 4 into delta R1 by R1. This equation we can also write the equation of delta R1 by R, that is in form of gauge factor. So we already know about the gauge factor is equal to delta R1 by R divided by delta L by L, right? So whenever change in length is going to be observed, we are going to observe the change in resistance. So V out is equal to V in G into E, that is our strain, that is delta L by L divided by the 4. So this is the complete output equation whenever we are connecting our R1 and R2. R2 is the compensating gauge. Okay, remember that over here. The bridge sensitivity is S is equal to V out by strain. So this is our bridge sensitivity, because strain, whenever we are going to apply some amount of strain to our gauge, at that time the variation in output is going to be observed, that is called as our sensitivity. So it is also, we can also write it like V in into G divided by the 4, because strain is going to be cancelled out. If I is the current passing through the gauge, then we can write V in is equal to twice I R1, and the sensitivity S1 in term of the bridge is given by S1. We are going to put the value of V in inside of the equation I R1 G divided by 2, because 2 is going to be cancelled out with the 4. So S1 by I is equal to R1 G by 2. So this is the equation in case number 1 for the sensitivity with respect to constant current. And now for the case 2, if R4 is compensating gauge, or we can say dummy gauge, and R1 is the active gauge, at that time same equation we can also write like sensitivity S1 by I is equal to V out by strain into I, or we can say P divided by 1 plus P R1 G. The current sensitivity can be higher than that obtained in case 1. Okay, in this session, in this case, the current sensitivity can be higher than the case 1. However, it indicates that a large excitation voltage is needed to maintain the same gauge current. Thus, temperature compensation can be obtained by using identical strain gauge expressed to same environment in either of the adjacent arm of the active gauge in bridge circuit. Okay. Now application of strain gauge, where we are studying and when we are going to use these applications, right? So they are used in electrical transducer device because of high accuracy and excellent reliability and ease of instrumentation. We can easily put it anywhere. Whenever we are going to use our strain gauge, we can stick anywhere to measure the strain applied on the object. Okay, the strain gauge are commonly used for displacement, pressure, force, displacement and acceleration measurement. A most common used of strain gauge is shown in figure. Over here we have one figure. In figure we can see R1, R3 and R2, R4 over here, and force is applied on beam over here. This is the fixed point, and due to some amount of mass of that object, the force is applied on the downward direction, and it is going to be observed on these different resistance, and output is going to be measured in between these 2 points. So it is a cantilever beam using 4 strain gauge. The gauge R1, R2 are subjected to tension, and R3, R4 are subjected to compensation. So these 2 forces are going to be expansion, R1 and R2, and over here R3 and R4 are going to be in compression load. Okay. The bridge obtain temperature compensation as the gauge are located at the same section of the beam, and they are exposed to same temperature environment, right? This circuit is used in all the transducer applications. If the specimen is subjected to loading F and load is perpendicular direction of N, then output voltage of the bridge is proportional to the bending momentum, okay? And the load N cause all four gauges to have same strain change in the resistance, that is delta R1 by R1 is equal to delta R3 by R3, because it is going to be loaded on the same axis, right? That is, we can also write like delta R1 N by R1 plus delta R1 F by R1. So F, that is the force, and N, that is the direction of perpendicular axis, right, is equal to delta R3 N by R3 plus delta R3 F by R3, because these both force are going to be same, as well as we can also write for R2 and R4. So delta R2 by R2 is equal to delta R4 by R4, and we can write something like delta R2 N divided by R2 plus delta R2 F divided by R2. Again, over here N is the perpendicular direction force and F is the subjected loading on the beam, okay, and is equal to delta R4 N divided by R4 plus delta R4 F divided by R4. The subscriptants N and F indicates the perpendicular and bending force, okay, and that is indicate perpendicular, and F, that is indicate the bending force. The gauge is symmetrically placed as V out is equal to 1 by 4 summation of delta R1 F by R1. Okay, this is the equation over here. I don't know why is equal to R here, but V in. So V out is equal to 1 by 4 summation of delta R1 F by R1 into V in. Okay, neglect this is equal to term over here. Now strain gauge calibration. The strain gauge are used in many applications where it is not possible to check the accuracy of the reading. After the strain gauge is bonded to a measuring position, it cannot be removed or transferred and subjected to known strain for the calibration. So once we are going to place our strain gauge to any surface, we are going to place it as a fixed, and then we cannot transfer it or remove it from that place, or we can say transfer it to the another place. However, it is led to error because the value of gauge factor is specified with some tolerance limit. We already studied about the gauge factor, right? Hence, each gauge needed to be individually calibrated. So, gauge need to be individually calibrated. Each and every strain gauge individually need to be calibrated. Simple strain gauge used readout system. Okay, readout system that have scale marked in arbitrary units. The objective of calibration of strain gauge is to establish the relation between arbitrary units and measured strain. Okay, it is actually measured what is the actual force applied on the strain and what is actual measurement we are getting. So it is the process of calibration of the strain gauge. Calibration of gauge deals with making adjustment to get correct reading. Okay, the method used in to produce a known change in resistance of one of the bridge arm to simulate a specific value of strain. If the unstrained resistance of gauge and gauge factor are known, then the change in resistance can be found out. The calibration process of strain gauge used a known change in the value of resistance of strain gauge by shunting it with a high value of resistance and then measuring out a corresponding to known change in the resistance. So we can also add up some extra resistance to get output that is vary with large scale. R01 is the shunted and the R1 is the gauge resistance as shown in figure. So over here we can see that RSH, that is shunted to our arm of arm 1, and S is the switch which is going to shunt, or we can say which is going to close these 2 points, that is between A and B. Now the resistance of arm 1 before S is closed, that is only Rg, and if Rg, that is this Rg resistance, that is arm 1, and arm 3, that is Rg resistance. Okay, now resistance of arm 1 after switch S is closed, so these two resistance are comes in parallel, RSH and Rg. So at that time we can write like Rg RSH divided by Rg plus RSH. The change in resistance of arm 1, that is we can write like delta Rg is equal to Rg, because in first case we have the resistance Rg when the switch S is closed, and then after minus when switch is closed, at that time the resistance, that is Rg RSH divided by Rg plus RSH. And we can also write in equation like R delta Rg is equal to Rg square divided by Rg plus Rsh. Now strain is indicated by 1 by Gf into delta Rg by Rg is equal to 1 by Gf. This is the simple equation of gain, okay, is equal to 1 by Gf into 1 by, we are going to put the value of delta Rg in this equation, 1 by Rg square divided by Rg plus Rsh, and this Rg is going to be cancelled out. So overall equation is going to be Rg divided by Gf, Rg plus Rsh, and shunt resistance Rsh is equal to, we can also define the value of Rsh in terms of this, from the value of this equation we can define the value of Rsh is equal to Rg 1 minus Gfe divided by Gfe. So this is the equation, or this is the value of shunt resistance we need to connect in our Wheatstone bridge. Now practically Gf into E, that is very much less than the 1, so we can neglect that. So Rsh is equal to Rg divided by Gfe, that is our strain. The value of strain can be found from this equation if a relation between output and strain is assumed. Only one value of Rsh is needed for calibration, okay, only one value needed for the calibration. This value must be chosen such that it give full scale deflection. So whenever we are applying a minimum amount of force to maximum amount of force, it need to be in full range. If there are n strain gauge element in the bridge, then strain is E, that is strain is equal to Rg divided by n Gf Rg plus Rsh. So this is the equation when we are connecting n strain gauge elements in our bridge circuit. And these are several questions that are very important with respect to your examination. So please note all these questions down, which we already covered in this video section. And if you have any kind of question regarding this topic, then please feel free to ask me in comment section. Thank you.